So welcome everybody to this talk here about supercontinuum generation with superior intrapulse coherence by tailoring the waveguide dispersion. So most of this work has been done by my postdoc Chao Mei, and I'm Günter Steinmeier from the Max Born Institute and the Institute of Physics of Humboldt University in Berlin. So quickly, the outline. I will start with introducing the concept of intrapulse coherence. Briefly talk about the mathematical definition of what is coherence in ultrafast optics. Briefly go over a numerical model that we use to simulate the propagation, discuss a number of waveguide designs, and then go quickly to the simulation results. And finally, I will wrap up with some conclusions. So intrapulse coherence is mostly important for the carrier envelope phase stabilization. So the carrier envelope phase is basically visualized here. So if you have a repetitive pulse train from a mode-locked laser, then you will typically find that the exact electric field structure does not reproduce itself from pulse to pulse, but there is an offset here of the phase relative to the peak of the envelope. And in this case, it was pi/2. And this translates itself into an offset frequency here in the spectrum, meaning you have an equidistant comb here. If you extend the equidistant comb lines towards zero, you will find that exactly at zero frequency, there is no component there. And in order to measure this carrier envelope offset frequency, you typically use F2F interferometry. And this heavily relies on a type of coherence that we refer to as intrapulse coherence. And this quickly gets lost if you have to broaden your spectra, and as almost any given laser has not sufficient bandwidth to directly apply this scheme, you have to think about how to do this in the best possible way. Now, coherence is a difficult thing. There are different definitions around, and in ultrafast optics, most people discussed interpulse coherence, which is some kind of correlation between successive pulses in a pulse train. This is not of interest here. This is mostly of interest if you want to compress your pulses into short pulses. What we need here is spectral coherence, as this is most relevant for the carrier envelope phase stabilization here. So this is correlation between two different frequency components, which are an octave apart, as you need them for F2F interferometry. Either definition here can be anything between 0 and 1, 0 meaning totally lost coherence, 1 meaning perfect coherence. So the noise model that we use is fairly simple. So we seed our simulations with a coherent waveform and add amplified spontaneous emission noise. And details on how this is exactly synthesized can be found in our recent Physical Review A, published in 2020. I don't say too much about this because this is kind of a standard thing, how to do this. So we use the propagation model. Also, I will only point out those things that are probably a little bit unusual here. So basically all publications that I've seen include dispersion, also nonlinearity here. In addition, we have a linear loss here because we sometimes go deep into the mid-infrared here. We included the Raman effect and also some spontaneous Raman emission, which can give rise to multiplicative noise, has been included here. Then the nonlinearity is included, including self-steepening and so on. And the variant of equation that we used here is typically referred to as a generalized nonlinear envelope equation, simplified version of Maxwell's equation. describing scalar waves up to second order. This is typically considered much more accurate than the traditionally used NLSE. It does not rely on the slowly varying envelope approximation. Okay, details can be also found in our publication here. This is all I want to say here. Now, we looked into different waveguides, and typically you would use microstructured fibers. What we synthesized here are different dispersion profiles, and we synthesized them by using solid fiber design consisting of cylindrical segments with different refractive index. And this allows fairly precise control of the group velocity dispersion profile. The same thing could also be done with photonic crystal fibers, but then this part of the calculation is much more elaborate, and in principle you would get the same results. So we have a standard profile here, single zero dispersion wavelength that's typically used for soliton fission scenarios. Then there is a second profile that has 2 zero dispersion wavelengths here. So this is the 2 zero dispersion wavelength profile. This is the standard here, the red one. And then we try to synthesize a super flat design here. This is this pinkish line here, which has 3 zero dispersion wavelengths, but it was made as close to zero as possible. We have then 2 normal dispersion profiles here, one which is rather flat and the other which has a slope here, additional slope. What is also shown here in the bottom part of the graph is the linear losses, which increase above 2 microns rapidly, and the varying nonlinearity. So the standard profile has a nearly constant or not overly strongly varying nonlinearity, whereas the more sophisticated profiles here actually have quite a dispersion of the nonlinearity here. Anyway, so simplest case here, the standard fiber, what is shown here, I have to walk you through this picture here. 4 cases each, 10 femtosecond pulses shown as a red line here, 100 femtosecond as blue, 200 as yellow line, and finally a 400 femtosecond. So the background of this is, okay, it's probably relatively straightforward to get coherence properties, good coherence properties with 10 femtosecond pulses, but somewhere beyond 100 femtosecond, this becomes increasingly difficult. Now, the first thing shown in A is the intensity. So this is basically the spectrum that you get. Then we have the 2 types of coherence. We should concentrate on the intrapulse coherence, but for completeness, we also shown the interpulse coherence that shows you the compressibility. This is relevant. The other coherence is relevant only for CEP stabilization. Then finally, we have something that we call a figure of merit. The coherence here may be quite high. For example, here, the red curve. But if the figure of merit is low, that means, yes, you have a high coherence, but you don't get a very strong signal. Ideally, you want to see here a very high value of the figure of merit. And at the same time, you want to see a good intrapulse coherence. And in this scenario, realistically, this is only given here in this very narrow range around 0.9 microns or so, that you get both things at the same time for basically pulses between 100 and 200 femtosecond. For 400 femtosecond, there is no coherence anymore. So this is the standard scenario. It is not very well performing. In contrast, now the best performance that we actually noticed was the flat or normal dispersion fiber. Again, the spectrum here, fairly flat here. You see in the interpulse coherence, basically perfect all over the range here. And the intrapulse coherence in this range here is also very, very good. And it comes with decent values here of the figure of merit. So this is really the best fiber that we found. But as always, there's a grain of salt here that you have to drive this fiber with much higher power than the simple, simpler 2-0 dispersion profile here that I've discussed before. So quickly, evolution of this intrapulse coherence during propagation. 2-0 dispersion wavelengths here, 100 femtoseconds on this side here, flat Andy versus 2-0 dispersion wavelengths. You can see that for the 100 femtosecond pulses, both cases are reasonably well behaved. So you get good coherence properties here in this range around 1 micron, broad range. For 400 femtosecond pulses, the flat Andy still works reasonably well, but there is no coherence whatsoever if you use the 2-0 dispersion wavelengths. So some conclusions. So maintaining a high level of coherence becomes increasingly complicated for longer pulses. There is a trade-off between the supercontinuum generation efficiency and the resulting coherence properties. And finally, high intrapulse coherence can be obtained quite short propagation for reasonably flat dispersion profile, but it comes at the cost of a high pump power.